Hello, welcome back to Math 155. Today we're continuing our discussion of discrete mathematics and continuing what we've been talking about so far with the principles of counting. So last time we met the idea of permutations. Today we're going to be thinking about combinations. Okay, so we'll also be thinking about something called the binomial coefficient, which comes up a lot, especially in probability theory. Okay, so what are combinations? So combination has a very specific meaning, just like permutation does. Combination is a set of objects that is unordered. So we have a set of objects and we take an unordered subset of those objects without repetition. Okay, so the big difference here with permutations is that with permutations, we care about the order in which we take things, whereas a combination, we don't care about the order. So if we take the set of numbers 1, 2, 3, if we care about the permutations, we care about the order. In the last lecture, we saw that there are 6 possible permutations. We worked this out by looking at 3 factorial, gives us our 6 possible permutations. There are 6 possible outcomes. But if we just care about an unordered subset of these objects without repetition, here we want to work out the all possible combinations where there are just 2 of these 3 numbers. Or can we have, well, we could take the first and the second one. That's one possible combination. We could take first and the third one. And we could take the second and the third one. And if I try to take the second and the first one, this is a different permutation, but it's the same combination of elements in this set. So 1 and 2 and 2 and 1. We don't want to have this one because we've already counted that combination. So this is for cases where you don't care about the order of things. So for example, if you go into a shop and you buy an apple and a banana, you don't care if you buy an apple and a banana or a banana and an apple, that's the same outcome. Okay, so we care about, when we talk about combinations, we don't care about the order in which we're choosing these things. So this is the all the combinations of 2 elements from the set 1, 2, 3. So how do we count combinations in general? Well, it turns out that this is closely related to our discussion of permutations, this P, N, K here. So remember, we have N different objects, and K of those objects are going to be taken at a time. And when we did our permutations, we cared about the order of those things. But here, we don't care about the order of these things. We want them to be unordered. So it turns out that this C, this combination of objects, when we take K objects from a larger set of N objects, is equal to our permutations that we can have divided by K factorial. So why is this the case? Well, if you think about if you've got a set of N objects, I'm just going to call these 1 to N, and we're going to take out of this a particular, we're going to draw K different things from here. So we can have A1, A2, and AK. In fact, rather than draw them out, these are just going to be a subset of these. So we're going to take K different things from here. If we think about the number of permutations that we can have, this is a set with K elements. So if we want to work out all the possible permutations from this subset here, we have K factorial possible permutations from this set. So if we have this set of N elements here and we take K elements from that and then work out all the possible permutations that we can have, this gives us a relationship between our total number of combinations of K objects from a larger set of N objects, or at least the same size, or larger, I should say, just to be clear. So it could be the same size if we have K is equal to N. We divide by our permutations, we get 1 over K factorial. So if we just multiply both sides by this PNK, then we end up with this relationship that we have here. Okay, so this C of n and k is written in this form here, where we have this long bracket here and an n and a k. So just to be clear, this isn't a vector, it's not a point, it is not n over k. This is actually read as n choose k. That's how we read this thing here. So n choose k is defined to be for any n greater than or equal to k greater than or equal to 0. We have n factorial divided by k factorial times by n minus k factorial. So why is that the case? Well, let's think about multiplying this out. We can multiply this out as n times by n minus 1 times by n minus 2 times by all the way down to n minus k plus 1 times by n minus k factorial divided by k factorial times by n minus k factorial. So at this point, we can cancel these factorials here, and this is the same as this, and we just have a k factorial on the bottom. So this proves that we can write our combinations of k objects from n objects as n choose k, which is n factorial over k factorial times by n minus k factorial. Also at the bottom here, we have some definitions of what goes on at the extremes. If we try to take 0 objects from a group of n objects, or if we try to take n objects from a group of n objects, we just end up with one combination. Okay, so we talked before about what happens if we try and take different colored balls from a jar without repetition. So suppose now we've got a jar that contains 6 colored balls, and we want to select just 4 balls from that jar. Now we can think about the permutations, which we talked about previously. Now we want to think about the different combinations. The permutations, remember, the permutations, the order matters. When we have combinations, we don't want to think about the ordering, okay? So for example, if I take red, blue, green, yellow, that is a permutation. Likewise, if I take blue, red, yellow, green, that is a different permutation, but these are the same thing when we think about combinations. So different permutations, but these are the same combination. So in this case, we need to just use our binomial coefficient from above. So we're choosing the combination where we have 6 objects, that's n is equal to 6. We're choosing k is equal to 4 of those objects. So we write this as n choose k, which is 6 choose 4, using the notation above, which was 6 factorial over 4 factorial times by 6 minus 4 factorial. If we work this out, it turns out to be 15. So there are 15 different combinations when we take 4 different colored balls without repetition from a jar that contains 6 different colored balls. Again, remember, these are unordered, so we don't care about the order, we just care about the end product of different balls that we get. Okay, so we've talked about different ways in which we can count things. Now we can think about different ways in which we can count them, but also combining this with our multiplication principle. So last time we had the example of ordering a pizza where we choose from 3 different types of crusts. So we have our crust choices, there are 3. We have 5 different topping choices, and you can either have the option of with or without cheese. And last time we looked at what are the different permutations when we have just one different topping. Now we're going to think about what if we have 2 different toppings? How many different choices can we have for this pizza? So that means that we need to think about the different combinations, because it's not going to matter in the order in which we put these things on. We're going to assume that the order doesn't matter here, whether you say choose pepperoni and onion, or whether you choose onion and pepperoni, the order doesn't matter here. So we need to think about our combinations of toppings, and we're choosing 2 from 5. So that means we need to look at the combinations where n is 5 and k is 2. So that's written also as 5 choose 2, which is going to be, we use our notation above, we have our n on the top, it's 5 factorial, divided by our k, which is 2 factorial, times by n minus k factorial. So that's 5 factorial divided by 2 factorial times by 3 factorial, which turns out to be 10. So this is our total number of combinations that we have. And we have 5 toppings and we're choosing 2 of those. So how do we come to our final answer here? Well, we just use our multiplication principle. So this was from the last lecture. Remember, we just multiply our possible outcomes. We have 3 possible cross choices. We have, when we select 2 different toppings from 5, we have 10 possible combinations. So that's just what we've worked out here. And then we have 2 possibilities for the cheese. So we have 3 times by 10 times by 2, which is equal to 60. There are 60 different choices that we can have when we select a pizza with 2 different toppings. Okay. Lastly, today we're going to think about what happens when we try to form different words from a word that has lots of repetition. So here we've got the word Mississippi, and we know that we have lots of repetition here. We have 4 I's, 4 S's, and 2 P's. And suppose we want to think about the total number of different 11-letter words that can be formed from the letters that are in this word Mississippi. You might say, why do we care about this? Well, this is just an example. You can think about sequences in the genome. If you have a sequence of TAGC, for example, G, T, T, and so on. If you've got a gene sequence like this, you might care about, with the limited alphabet that we have here, you might want to care about what types of different sequences can we get from this, but we don't want to count sequences that if we just switch the order of these T's around, that's a different sequence, okay? So we care about these different orderings. Okay, so let's think about our word Mississippi. Well, we have 4 different I's, we have 4 S's, and we have 2 different P's. And let's think about what are the total number of permutations here. If we gave each of these different I's as being a different I, if we just treated them differently to start with, if we think of our total number of permutations, so that's, we have 11 letters in Mississippi, so our N and our K in this case are the same because we're trying to choose a permutation with all the letters in Mississippi. This is going to be 11 factorial if they were distinct letters. But here, we want the actual number of different words. I'm going to use words in the previous context that we used them in the sense that these are our sequences of letters. They don't have to make sense as an actual word in the English dictionary. So the actual number of different words, well, here we have what's our total number of permutations divided by our number of repetitions for the same word. And what's that going to be? Well, we have 4 I's, 4 S's, and 2 P's. So every time we have, if we write out a word Mississippi, every time we change a P around, or say we change an I around, we're not going to count that as a different word. And same with our S's. If I switch these letters here, that would still give me Mississippi, so it's still the same word. So I don't want to count this because I want different words. So in this case, we're going to start with our 11 factorial on the top, and then we divide by different permutations. So we have 4 factorial permutations for our I's, 4 factorial permutations for our S's and 2 factorial permutations for our P's. So we now need to divide by the product of these. So 4 factorial times by 4 factorial times by 2 factorial. And that will give us our outcome. Again, I'm not going to calculate that here. The key thing is about how we actually work this out. Okay, so this is just an example to illustrate how we can account for repetition in our objects in a set. Our objects here are our letters, and our set is the set of letters in Mississippi, and we are accounting for the repetition of those objects within this set. We don't care about it really in the real world when it comes to letters and words, but we will care about it when we think of things like sequences and other things related to, say, amino acids and combinations of those that we can have when we form peptides. Okay, so that's it for today. We'll go through some of these problems in class.